This is the second part of the 8.3 lecture, where we're going to take a closer look at the dual nature of the electron, Heisenberg's uncertainty principle, and the de Broglie formula. Let's begin. In Chapter 8, we've been discussing the wave-particle duality of light. If we consider a beam of particles aimed at two closely spaced slits on the left, we see two bright spots where the particles hit the dark screen. If we consider the electron beam going through the same two slits in the experiment on the right, however, we get an interference pattern similar to what was observed for light. Like light, we see electrons have this dual nature of behaving like a particle and a wave, but not both simultaneously when the electron is being observed. In fact, according to quantum mechanics, electrons occupy both states, behaving like a particle and a wave when they are not being measured or observed. This means the electron can actually interfere with itself and pass through both slits simultaneously. So that's tough to wrap your head around. However, we need quantum mechanics to explain multi-electron atoms because the Rutherford and Bohr models fall short. We can do so if we keep the Heisenberg uncertainty principle in mind, which explains we can either know the momentum or speed of a particle or its position. So why is that? In simplest terms, it's a matter of scale. If you bounce a radar beam off a car in a known position, you can accurately gauge the velocity. The car moves on unaffected. Attempt to do the same thing to an electron, and you're going to affect it. You want to know the speed, you can measure it, but the electron will be knocked off its original path. Heisenberg's uncertainty principle, as applied to our electron beam double slit experiment, allows us to see the particle nature of an electron by placing a laser beam directly behind the slits. When an electron passes through the slit, it causes a photon from the laser to flash as it's scattered by the electron. Essentially, this is allowing us to observe which slit the electron is passing through, which forces the single electron to pass through one slit or the other as if it were a particle instead of a wave. So the laser allows us to see the particle nature, while removing it allows us to see the wave nature of the electron. It's truly a fascinating physics and thought experiment. Mathematically, the uncertainty principle states that the uncertainty in position, delta x, and the uncertainty in momentum, mass times delta velocity, must be greater than or equal to Planck's constant over 4 pi. For you, this equation's relevance lies in the fact that the more you know about position, the less you know about an object's velocity. The de Broglie wavelength finds greater utility in general chemistry. We can calculate the wavelength of any object using Planck's constant, the mass of the object in kilograms, and the velocity of the object in meters per second. Let's try an example calculation. Let's start by calculating the de Broglie wavelength of an electron. Matching our values in units to their respective variables, we see that m equals 9.109 times 10 to the negative 28th grams, which we need to convert to kilograms. The velocity, v equals 19.2 meters per second, is expressed in the proper units. Putting it all together, we get lambda is equal to 6.626 times 10 to the negative 34th joule seconds divided by 19.2 meters per second times 9.109 times 10 to the negative 31st kilograms. So how are these units supposed to cancel out to give us meters? Joules are a derived unit, meaning 1 joule is equal to 1 kilogram meter squared per second squared. This becomes a complex fraction where everything winds up canceling out except for the meters. Our answer is 3.79 times 10 to the negative 5th meters. So how does an electron's wavelength compare to that of a baseball? A baseball is much heavier, so we'd expect the wavelength to be much shorter. Let's find out. What is the de Broglie wavelength of a 148.8 gram baseball traveling 41.4 meters per second? If you didn't get answer C, then make sure you converted grams to kilograms and check all of your arithmetic. That's all for this lecture.